Okay, so we shall start this tutorial session, right? So the course, as we all know, is Fundamentals of Compressible Flow, being conducted by NPTEL, right? So the instructor for this particular course is Professor Niranjan Sahu, and he's from IIT Guwahati. And my name is Aditya Sharma. All right, I am a Prime Minister's Research Fellow and a research scholar, a PhD student here at IIT Guwahati only. So for this particular for these tutorial sessions, I will be the teaching assistant. So I will be taking these tutorial sessions, live tutorial sessions for this course of for this course of the lectures. All right, for the period of this whole course, Fundamentals of Compressible Flow. In total, I'll take 13 tutorials, right? So 13 live sessions I'll take, and in that series, this particular tutorial is the beginning. It's the first tutorial session. All right. So we shall then move forward towards our today's session. So the course of this session will be as follows. So firstly, I'll just brief you all about the content that has been taught in week one in the lectures, video lectures of week one, and then based on the concepts learned in week one. Uh, I have some set of questions. So the questions, the nature of questions is uh, theoretical as well as numerical. So for the theoretical, we shall have discussion. All right. And then for the numerical type of questions, we shall try to solve such questions. Okay. So the topics covered in week one, let's discuss these one by one. All right. So first topic that was covered, first topic that was covered in lecture one of this course was concept and definition of fluid. All right. So as we all know that the course is fundamentals of compressible flow. So basically here we are trying to study a kind of fluid flow, right? That is compressible. So we have started the course with basic definitions of fluid and their properties. All right. So how do we define a fluid? So all these small things have been covered in the first week lectures. So first topic, main heading that was covered was concept and definition of fluid. So in this topic, we saw how fluids as state of matter, how do they differ from solids? All right, the arrangement of molecules in the case of fluids with respect to solids. So how do they differ? All right. So arrangements we discussed in lecture one. Uh, then came the second topic, which was properties of fluids. So how do we define fluids in terms of their properties? So we discussed, we saw that in lecture one, right? So different properties were discussed, right? So properties like properties, thermodynamic properties like temperature, entropy, enthalpy. All right. Such properties briefly discussed with respect to fluids. And then equation of state of uh, gases, that was also discussed in the lectures, right? Then kinematic, then some uh, kinematic entities related to fluids were introduced in the lecture one. All right, in the following slides. Then the transport properties. So in transport properties, we basically are concerned with movement. All right, movement of mass, movement of momentum. So diffusion related terms were discussed in the lecture, right? Then there were specific or miscellaneous properties like pressure of a liquid, right? Then bulk modulus of a fluid, all right? And then speed of sound as will be taught in the coming lectures, in the coming weeks. So speed of sound is a very important speed of sound is a very important parameter, right? So based on which various things uh, like speed of sound is a very important parameter as far as the compressible flow is concerned, or compressible flows are concerned. All right, so that also shall be seen in the coming weeks, in the lectures of coming weeks. All right. So after that, after covering the properties of fluids, so fluid statics, some basic terminology related to fluid statics were taught. All right. So what is a hydrostatic condition? So if the flow is not in movement, in that condition, we call that fluid as hydrostatic, right? So related to uh, such situation of the fluid, one law was also introduced, which was Pascal's law, right? Pascal's law basically, as you all must be knowing, that it's related to the pressure of the fluid, and the fact that the pressure at various locations is not dependent on the direction uh, on the direction in the fluid, right? So basically it was like this. So if we see, if there is this, let's say there is a fluid in this container, right? So if at some location you see, right, at these two locations, because when the fluid is not in motion, the pressure will be same. But is this won't be case with the fluid dynamics, right? When the fluid is in motion, we cannot very generally deduce this. But as per Pascal's law, this would be the case. All right. Okay. Then there is next topic was classification of fluid flow. So in classification of fluid flow, we saw the fluids, various types of fluids and their categorization. All right, the categorization based on some particular theme, the fluids were categorized, and that was discussed in this very topic. So fluids were categorized based on the viscosity, based on whether the density variations are significant or not, based on whether the fluid is changing with respect to time or not, based on the Reynolds number, right? And then at last there was natural and forced flows. All right. Sorry. So such categorization was this for viscosity theme. There are two categories of fluids. One is inviscid, that is there is no viscosity, and then there is viscous flow, right? Then for density variations, there is incompressible where there is no density variation, right? And then compressible where there is density variations are prominent. Then based on whether the flow is changing with respect to time, if the flow is not changing with respect to time, it is steady, all right? And if it is changing with respect to time, then it is unsteady, all right? Then laminar and turbulent flows were discussed. So uh, for some particular Reynolds number, below that value of Reynolds number, the flow remains laminar, and beyond that it starts to transition towards turbulent, and eventually if the Reynolds number is further increased, the flow becomes turbulent, right? Then this natural and forced convection were discussed uh, in the lectures, all right? Okay, then I believe these were the topics which were covered in lecture 1, all right? Then after that, a very important concept as far as the fluids are concerned. So it's basically a supposition that the flow is in continuity, all right? So for the mathematics of the fluids, it's a very important supposition that is to be considered, right? Because in reality, if we see the structure of fluid, so every matter is fundamentally is molecules, right? So there are spaces between molecules, right? But when we have to deal with the mathematics of the fluid and the scale we are interested in of the fluid, right? So the scale we are interested in of the fluid, if that scale is very large in comparison to the spacing between the molecules, or in very precise terminology, if we see the mean free path, right? So with respect to mean free path, if the scale of the fluid we are interested in, if it is considerably high, so in that case we call that fluid as continuum. So our supposition holds for that case. Sorry. So to define whether a flow is continuum or not, we take help of a number which is Knudsen. Okay, Knudsen number. So this is has been mentioned here also. So it's basically is the ratio of the average mean free path and the fluid scale we are interested in. We are interested in. All right. All right. So for fluid to be continuum, as has been mentioned in the lecture 2 slides, so it has to be Knudsen number has to be less than, all right, 0.0. 0. Okay, right. Then in the later slides, defining fluid, how do we define fluid was considered. All right. So in this scenario, the Lagrangian and Eulerian descriptions were given. All right. Then Reynolds transport theorem was also discussed. Okay. And then a very important uh, uh, tool, all right, total derivative was discussed. So total derivative is basically a sum of local derivative and, let me write this here, total derivative is local derivative plus convective weight. So basically, what local term is related to is time. All right, the variations in a particular property with respect to time, that is a local derivative, and then if and the variations with respect to the position of a particular property, we call that as convective derivative. All right. So later also there is one question also related to this. So we shall see how we can solve that particular question. All right. Okay. Local derivatives and convective, local derivative and convective derivative. Then so this is covered, right? So then pressure and temperature fields were mentioned in the slides further. Uh, okay, very basic and important properties. Then next, body and surface forces were discussed. So in momentum equation of the fluid. Okay, so in the momentum equation of the fluid, these forces are considered because when we are dealing with flows, all right, when any type of fluids, basically a fluid dynamics problem. Okay, so in that we have to consider momentum equations, right? So fluid has some momentum, and then we are trying to make sense of that momentum using the momentum equation, right? So because it's a fluid dynamics problem, so forces are to be considered just like considering the velocity or acceleration terms, or the mm, distance terms or displacement terms, that won't suffice as far as the fluid dynamics is concerned. So forces are also to be taken into consideration. So in that situation, body and surface forces come into picture. All right. So example of one very good example of body force is gravity. So the body force, as the name suggests, body, right? It is related to body. So it is related to the body of the fluid. So gravity is one such property which is by the virtue of the body of the fluid it acts, right? As we all know. So gravity is one good example of body force. Then there are surface forces that are of utmost importance, right? So pressure forces and shear forces. These two forces come under body force. All right, body forces. So uh, these are the forces, okay, in the momentum equation. Then finally governing equations for the fluid flow were discussed. All right, so governing equations, continuity equation, right, which is nothing but the conservation of mass equation, right? Then there is momentum equation. All right. So momentum equation is nothing but second Newton's second law, right? Force equals to mass into acceleration. So here the force is nothing but body and surface forces that are acting on fluid, and the impact of these forces is the change in the velocity field of that fluid. So if we know the velocity field of a particular fluid, if we are able to figure out the velocity field of a particular fluid, then our problem for that flow is solved. All right. So then we know the behavior of the fluid. Okay. So uh, that is uh, momentum equation, right? Then there is energy equation, right? So it's based on thermodynamics laws, like, all right. So like first law of thermodynamics, second law of thermodynamics, based on these, the energy equation is derived. All right. So this is basically nothing but conservation of energy equation. Okay. Then there are transport equations also. The like it has been discussed in the lectures, diffusion is one such phenomena where there is transport of momentum, mass, all right, or heat. So when that has to be considered in that scenario, transport equations are very helpful. All right. Okay. So this was about the topics that were covered in week one, lectures of week one. All right. Then, then I believe we can proceed forward. All right. We can proceed forward with the questions that that I have for this session. So one by one, we shall see those questions, and we shall try to solve them. All right. Okay. Okay. So the first question we have, the fluid is defined as a substance in which, so we'll have four options, and uh, looking at those four options, we shall try to see which one is the apt uh, option for this particular statement of the question. All right. So, so the fluid is defined as a substance in which the stress is proportional to strain. So it's saying the stress is proportional to strain. Stress is proportional to strain. All right. So stress proportional to strain basically is for solids. Okay. Then strain rate is proportional to stress. That doesn't make sense to us. All right. This statement doesn't make sense to us. All right. Then strain is proportional to stress. That also doesn't make sense to us. All right. Because in proportionality also, which thing is first and which thing is the next is very important. So stress is directly proportional to strain is not same as strain is proportional to stress. All right. So we know stress is proportional to strain for solids, but here the question is for fluids. All right. So we have to answer keeping in mind fluids. All right. Then fourth statement is stress is proportional to strain rate. So for this particular question, this fourth statement is the right one. This has been covered in the lecture 1 also. So this is one important difference between solids and fluids, is that stress here is proportional to strain rate. So there is in in case of solids, when there is stress, there is a constant strain linked to that stress. But in the fluids, it's not the case. If there is stress, there will be strain. Also, the strain will not be constant, it would vary. So the rate of that strain has needs to be taken into consideration. Only then we will be able to uh, put things in perspective in mathematical form for fluids. All right. Okay. So let's see the answer of it. So yes. So the answer is uh, D option. Okay. So this option of ours is correct. All right. Sorry. Then let's move on to the next question. All right. This question is over. Okay. Okay. So the generic expression for of a flow field satisfying the continuity equation. The generic expression of a flow field satisfying the continuity equation. So here a expression has been given which is satisfying the continuity equation. All right. Is represented as del dot rho v equals to 0. Identify the correct statement. So now we shall see the options linked to this question. Okay. So there are four options are there. The flow is steady and uniform. All right. It's steady and uniform. So I have already discussed that flow is steady when the uh, time terms are not in the picture. All right. Okay. The flow field is second option is flow field is compressible. So flow will be compressible if the density terms are changing with respect to either position or with respect to time. All right. So the flow is steady. All right. And the flow is incompressible. Okay. So here in option in this expression, if we see, so this is del. If you see, del is nothing but all right. So this is del. So now we are doing its dot product with respect to rho and with respect to. So here rho is a scalar. All right. Rho is scalar, but we cannot directly consider that rho is constant, right? Rho can be dependent on the position of the fluid element, right? So if the fluid element is changing its position with respect to that, the density can vary. So it's not given in the question that rho is constant, all right? So in that case, if rho is being considered in the expression, then this this flow is obviously compressible, right? Also, because the time terms like dou rho by dou t, because this is the full expression for the continuity equation. So this thing is zero here, right? All right. So because it's not changing with time, so I believe it can be also said that the C term is also right. All right. So B is there, but the flow is, I believe, also steady. But we shall confirm this in the next session. All right. But I believe C should also be there. But I shall confirm this. All right. Okay. I just figured this out. All right. But okay, but B will definitely be there. But I believe C should also be there. But okay, here I have B as the correct answer. But I shall look into this question. Okay. 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 So this is how we dealt with question number 2. All right. Then, then we have this question. Uh, the velocity field is represented as V equals to this. The expression for the acceleration at, we have been given one location. All right. One location has been given where x equals to 2, y equals to 4, and z equals to minus 4. All right. And then t is also given. Okay. So we have a velocity field which is a function of x, y, z, and t. And then we have been given one position, and then time also, a particular time has also been given. Sorry. So based on that, we have to solve this particular problem, right? So options are also given in this particular problem. So we shall try to solve this. Okay. So as I have already mentioned that this is a, okay. So this is question number 3, solution. Okay. Okay. So in question number 3, uh, let's just try to solve this. So what we will do is, so acceleration has been asked, right? So here we will use d by dt. So this term is total derivative, right? As I was discussing earlier, all right, of v. So the velocity field, total derivative of velocity field, we shall figure out, and based on that, we will be able to solve this problem. All right. So equals to del. I have already told. Okay, what del is? Sorry. Okay. So if we compare our velocity field with ui plus vj plus k. Alright. Then we have u equals to 4 plus xy plus 2t. Alright. And v is 6x cube. Alright. And then w is 3x t square plus z. Okay. Okay, so one by one we shall solve these two terms. All right. So first uh, we will. Okay, if we see del v by del t, all right, it is nothing but 2 I cap plus 0 j cap plus 6 x t k cap. All right. So this is our local derivative, which is for the change in the velocity field with respect to time for a particular fluid element. All right. And then, because it's a general equation, so you can say it's the whole flow field. All right. Rather than saying a particular fluid element, it's a uh, flow field. All right. Then we will try to see how to solve this. All right. So this is nothing but by dou x. Sorry. Plus v dou by plus w dou z. Okay. This is this term. Okay. And then we have our velocity term. Okay. So if we try to solve this, right? So what we get is we just initially we'll just uh, this differentiate using these operators. All right. So del by del x, del by del y, del by del z. We shall solve this. Plus. Right. Okay. So this we have got. All right. Now we will put the values of uv and w that we have here. Uv and w we have here. So we will these values. Right. We will use these values in our expression, in this expression that we have got. So what we will get is equals to plus I cap plus J cap. Okay. So we have got this expression. All right. From here we have this. Okay. In terms of x and t. And then for the convective, this is convective derivative. Derivative. This is also in terms of x, y, z, and t. All right. And the values of x, y, z, and t are already given in the question. Okay. So if we see the question, it's given here. All right. So these values already been provided in the question. Okay. All right. So if we put these values in both the derivatives, like local derivative and convective derivative, so we get acceleration equals to, if we just figure this out, right? This is our answer. Okay. So this is how we can solve this type of question. Okay. So second option, B option. Second option is the correct option. Okay. So this way we can solve this. Okay. Now we shall move forward with the session. All right. Okay. So here we have question number 4. Question number 4 says that a solid rubber ball has its volume reduced by 15%. So we have a rubber ball. So its volume has reduced by, solid rubber balls, volume reduced by 15%. Okay, when subjected to a uniform stress. Okay, so uniform stress of 15 kilonewton meters square. Okay, Newton meters square. The bulk modulus in Newton per meter square. Sorry, Newton per meter square for rubber. So question is, what is bulk modulus? It's a numerical type question. All right. and bulk modulus has been asked. Okay. So what is given? The volume has reduced by 15%. Okay. So we know bulk modulus. The formula for bulk modulus is minus V dP by dV. All right. Okay. And but here the initial volume of the solid rubber ball has not been given to us. All right. So what we will do, we will just suppose that uh, its volume is V. Okay. Because it has been mentioned in the question that the volume has reduced. So if the volume has reduced by some percentage, so to numerically show that we will have to take some reference volume. All right. So we will suppose that let volume of rubber ball V. All right. So the volume has reduced by 15%. All right. So if we see the change will be okay. Let's do it this way. So reduced volume is 0.15 V. All right. So if we have to write dV, how we will write dV? It will be same, but just a negative sign will be added to the this value because the change is in reduced form, right? Right. The volume is not increasing. Had the volume increased, the sign would have been positive. All right. So if we figure this out, all right. Okay. So if we figure this out, all right. Sorry for the noise if you're getting in the background. I don't know for how long it will be there, but we shall have to proceed with it. Okay. All right. So now we'll just okay. So we'll just find out the bulk modulus now, right? So bulk modulus is as has been mentioned, is minus v dp by dv. All right. So minus v dp here is 15 kilopascal. That is 15 into 10 raised to 3, right? And then dv is minus 0.15 v. All right. So minus and minus will cancel out, and what we will get is, and v also will cancel out, and what will remain is 15 into 10 raised to power 3 divided by 15 into 10 raised to power minus 2. All right. 15 and 15 will also cancel out. What will remain is 10 raised to power 5, and that is our answer. All right. So if we see the options, okay. So there are options. Let me just show you. There are options. 4 options are given. Clearly, we have the answer. Option C is correct. All right. So let's check the answer. Yes, answer is given here. All right. Here, here is our answer. All right. Here is our answer. It's just 10 raised to power 5. All right. So this way we solve this particular problem. All right. Now we can move on to our next question. All right. So the properties that bear the relation to movement of mass and momentum and heat for a fluid are called as. Okay. So here what the question says is that there are a set of properties, and those properties bear relation to, so those properties are concerned with the movement of what? Mass, momentum and heat. So as I was discussing it earlier also, so when we are concerned with the movement of mass, of a chunk of mass, or the moment or the momentum related to that mass, or the heat that particular mass of fluid is carrying, when we are concerned with such movements, all right, then in that scenario we call such properties by particular name. All right. So first we shall see the options linked to this question, and then try to answer this particular question. All right. So first we have been given thermodynamic properties. Thermodynamic properties, in thermodynamic properties, we deal with temperature. All right. We deal with enthalpy, specific entropy, or just enthalpy, or just entropy. All right. So these things are considered in thermodynamic properties. And in kinematics, we have studied, I believe, in class +1 or +2, we have studied this. All right. So there used to be 3 kinematic equations. All right. V equals to U plus AT. Right? S equals to UT plus half AT square. Right? V square minus U square equals to 2S. Such equations used to be there for kinematics, right? Where we are concerned with the velocity, displacement, distance covered, all right, acceleration, initial velocity, final velocity. So that is kinematics. And with respect to fluid also, such if such parameters are to be considered, then it becomes the kinematic property related to particular fluid or particular fluid flow. All right. Then, so that is not what the question is asking. All right. Question is dealing with momentum also. All right. Mass, movement of mass, movement of momentum. All right. It's not just concerned with velocities or not just concerned with temperature or enthalpy or entropy, right? Not just heat terms, not just thermodynamic terms. All right. So the third option is transport properties. So transport is very much linked, sorry, to what has been asked in this particular question. All right. So transport properties, we deal with the movement of uh, mass or momentum or heat. All right. And the diffusion, one example of this is the diffusion of two gases that has been discussed in lecture 1, I believe, at the end of lecture 1, yes. Right. So then there are dynamic properties. Right. So we have a clear-cut uh, answer to this. All right. See. Okay. So dynamic properties uh, is not the uh, answer linked to this question. So the question has asked the movement of mass, momentum, and heat, and transport properties clearly. The these movements of mass come under this transport properties umbrella. All right. Okay. So the answer is transport properties. Okay. All right. So then we move on to our next question. All right. I believe it's almost 1 hour. Almost 1 hour has passed since this session started. So we shall, I believe, take a 5 minutes break, and then the session shall continue. All right. Okay then. All right. So since we have taken a break, 5 minutes break, so we shall again continue with the session. All right. So in front of us, we have question number 6. Let's check this out. So question number 6 says the Pascal's law is applicable to the liquid, which is, so I believe we have options related to this question. So yes, we have 4 options. Sorry. So Pascal's law, as I have already discussed, is concerned with the fluid statics. All right. So Pascal's law is applicable to the liquid, which is option A says that it's incompressible, right? Second says that compressible, or both, or none of the above, right? So the correct answer for that this is incompressible flows, right? So if the flow is incompressible, the Pascal's law is applicable in that scenario. Okay. Okay. Then we move on to next question. So this one is a numerical one, right? So let's see this. The ratio of densities of oxygen and nitrogen. So densities are given, right? Ratio of densities of oxygen and nitrogen is this 20 is to 18. The speed of sound in nitrogen gas at 21 degrees Celsius is equal to speed of sound of nitrogen gas at 21 degrees Celsius is equal to speed of sound in oxygen at certain temperature. So for nitrogen gas, it was 21 degrees Celsius, and for oxygen, we don't know the temperature. And speed of sound is being mentioned here. All right. So the question also has been asked this. All right. That the temperature in Kelvin in oxygen gas is. All right. So this has been asked. So let's uh, jot down what has been given to us. All right. So density ratios are given. All right. This is given. We know density equals to mass by volume, right? Okay. And then what is given? T of N2 is given 21 degrees Celsius. Because when we have to deal with the mathematics of temperatures, then it has to be converted into SI units. Only then the mathematics will be correct. So for that, we know we can easily convert it by adding 273 with it. So it comes out to be Kelvin. All right, 294 Kelvin. Okay. So now it came out to be 294 Kelvin. All right, and temperature of O2 is not given, and that is to be found out. Okay. Okay. What else? So if the we consider the same volumes of nitrogen and oxygen, then what can be deduced is, okay, I believe we should solve this here only. Okay, this was question number, let me check the question number 7. All right, so this is question number 7. All right, its solution. So rho of O2, rho of O2, rho of N2, rho of O2 by rho of N2 is given 20 by 18. So if we write it as m of O2 by V and m of N2 by V equals to 20 by 18, that implies m of O2 by m of N2 equals to 20 by 18. Right? What else is given in the question? It's given that the speed of sound, alright? Speed, we represent speed by A, alright? Speed of sound in nitrogen gas at 21 degrees Celsius. So at 294 Kelvin equals to speed of sound in oxygen at some T. All right. So the formula for speed of sound is A equals to gamma RT by M. So using this, we can say gamma R Tn2 by Mn2. Right? Gamma R TO2 by M02. Alright. I'm squaring both sides. Squaring both sides. What we get is gamma RTN2 by Mn2 equals to gamma RTO2 by MO2. Okay. So these will cancel out, and now we'll place T in one side, TO2 is one side, and all other things are on the other side. Alright. So MO2 by Mn2 into Tn2. Alright. So Tn2 is given, and this MO2 by Mn2 ratio is given here. All right. Okay. So we will write it this way: 20 by 18 into T94. So now if we try to figure this out is using calculators. So this comes out to be 326.67 Kelvin. Right. So this is our answer. Okay. So this came out to be 326.67 Kelvin. So if we check out our answer, if you see the answer, So it comes out to be between this range. So it was a range type question, so range had to be given. So our answer falls out in this very range. Alright. Okay, this is our answer. Okay. Okay. All right. Now let's move on to next question. Okay. So now we are in question number 18. Question number, sorry, 8. So the question is like this: the property of fluid viscosity decreases with increase in temperature for a liquid and increases with increase in temperature of a gas. So there is decrease with increase in temperature for liquid, and there is increase with increase in temperature for gas. So the question is whether this statement is correct or not. So it's an observation and it's also a fact that when the temperature increases in liquids, its viscosity decreases, right? And in gases, when the temperature is increased, so the randomness of gases also increases, and which creates friction in between the molecules, and eventually which leads to increase in the viscosity of gases. So this statement is very much correct. All right. Statement is very much correct that there is decrease in viscosity with the increase in temperature of liquid, and there is increase in viscosity with increase in temperature of gas. All right. So this is the answer. All right. It's right. Now we shall move to next question. All right. So this is a paragraph type question in which we have been given some set of values, and based on those values we have to find out the uh, we have to figure out how to solve the questions based on which have been given and which are based on this particular paragraph, the values given in this particular paragraph. Okay. So the paragraph says the argon gas. So we have been given argon gas. Let's underline these things, right? What the question says. So we have been given argon gas, and then characteristics. It's sorry, it's not characteristics, but characteristic. And the characteristic gas constant is given 208. All right, joule. It's in its SI units, and then specific heat is given. All right, this we denote by R, and then specific heat ratio we denote by gamma. So argon is flowing through a tube, it's a flow, all right, with the initial pressure and density conditions initial pressure, all right, and density are given. So for argon, P1 is given, right, which is 1.7 into, let's just, because it will be a lengthy or maybe slightly lengthy. So we'll just jot these things down in our sheet. So this is question number 9 solution. So we have been given P1 equals to 1.7 into 10 raised to power 6 Pascal, all right. And then density is also given. What is density is given? 18, all right, 18 kg per meter cube. Okay, this is given. All right. So then what is given? Gamma and R values are also given. All right. So R is given 208 in SI units. All right. And gamma is given 1.67. Okay. So these things have been given. And the final pressure and temperatures are given. All right. So final pressure is given 248. All right. 248 what? 248 kilopascal. That is 248 into 10 raised to 3 Pascal, or 0.248 into 10 raised to power 6 Pascal. All right. Okay. And then temperature T2 is also given, which is 400 Kelvin. All right. Now, these things have been provided to us. All right. Now let's see what the question has to say. All right. So the change in enthalpy in joule per kg for argon is. So now the question asks for the enthalpy, change in enthalpy, right? So we need to find change in enthalpy in joule per kg. So change in enthalpy is to be found out in joule per kg. Okay. So first of all, we know that what is Cp. All right. Cp is dou H by dou T at constant pressure. All right. So from here, the change in enthalpy can be found out. All right. But for that, we need two things. One is this, we need to find out change in temperature, and then this value. All right, the specific heat value at constant pressure. Heat value. So we have a formula for specific heat at constant pressure, gamma by gamma minus 1 into R. All right. So here gamma is 1.67 and this comes out to be gamma minus 1 comes out to be 0.67 and R is 208. And the whole thing comes out to be 519 joule per kg Kelvin if we try to figure this out. All right. Okay. So this was CP, and then here if you see T2 is available, right? But to figure out the change, we need T1 also. So how do we find T1? So we know from the perfect gas equation, right? From the rho RT, right? So if we take this like this, we have T1 as 1.7 into 10 raised to power 6, and gamma also we have 18, right? And R we have 208. All these values are in SI units. And then T1 we don't have. So if we calculate this, we'll get our T1 value. So let's calculate this, right? So 1, 7 divided. So this comes out to be 454.06. All right, Kelvin. So change in temperature now we have as T2 minus T1. All right. Which is 400 minus 454.06. That is 54.06 Kelvin. Okay. Minus 54.06. So our change in enthalpy comes out to be change in enthalpy comes out to be Cp into del T, right? This is del H. This comes out to be 519 into minus 54.06, and this comes out to be, let's just figure this out, 590. Okay, so this is minus 28057.14. So this is our change in enthalpy, all right? Joule per kg. Okay, all right. So this is our change in enthalpy. Okay, and if we see our answer, so yes, this our answer is in this range only, right? All right. So we solved question number 9, which was about change in enthalpy for the given gas, which is flowing through a tube with its initial pressure and density given, and the final pressure and temperature given, right? So we first found out the specific heat at constant pressure. Then we found out initial temperature of the gas using the perfect gas equation. And then uh, when we had these two values, we could easily calculate the change in enthalpy. All right. Okay. So moving on to next question. Okay. So here it should have been entropy on it. So the change in entropy in joule per kg for argon is. So the question here asks for change in entropy. All right. Unit also here it should have been joule per Kelvin. Okay. All right. Because when we are dealing with specific quantities, specific entropy or specific enthalpy, then mm, it's with respect to its mass. All right. So it's divided with its whole mass, and then we give the value of specific quantities. All right. So the unit also says a lot that what has been asked. All right. So this has been asked that we need to find the change in entropy, right? So let's work this out. All right. So the change in entropy's formula is Cp ln T2 by T1 minus R ln P2 by P1. All right. So we already have the value of Cp, and the value of T2 is given as 400 Kelvin, and for this it's given as 454. T1 we have calculated as 454.06 Kelvin, and R is given to us 208, and pressure also P2 was 0.248 into 10 raised to 6, and P1 was 1.7 into 10 raised to 6. All right. So we shall figure this out. So first, let's find out the first term. Okay. Okay, the first term comes out to be minus 65.79. Right. And the second term, let's figure this out. Work this out also. Okay. So it comes out to be minus of 400.39. All right. So which will become positive. Right? So now if we work this out, it comes out to be 334.6 joule per kg Kelvin. All right. Okay. So this is the specific entropy change. So if we see the answer given for this, so this is given. The range has been given 333 to 336. So our answer lies in this range only. So we have solved this question correctly. All right. Okay. So these were the 10 questions, and these questions are from previous year assignments. All right. So this course ran in the year 2020 also. So these set of questions, first 10 set of questions. All right. So these were from that time only. Okay. And beyond this, uh, from the lecture slides, I have uh, prepared some fill in the blanks. All right. These all questions are theoretical in nature, just to revise the concepts. All right. From this perspective, the fill in the blanks have been prepared so that we can revise the basic concepts that have been covered in the week one. Okay. So in the following questions, we shall see such questions. All right. So let's move ahead with the session. Okay. All right. So question number 11 says qualitatively the stress is proportional to strain for solids, but in fluids the stress is proportional to. So this question we have already covered, right? So here it's in fill in the blank form, right? So it's proportional to strain rate. Okay. So this I have already discussed in one of the previous questions. So let's see this answer. Yes. So the answer is this only. All right. Okay. So let's move ahead with the next question. So the question says when the vapor is at saturated state, the pressure that vapor exerts on the liquid surface is called as. All right. So when in a closed system, a liquid and its vapors are in equilibrium. All right. Also, there is such a situation that the vapor have come to its saturation and no further vaporization of the liquid can take place beyond that particular stage. So in that case, the pressure that a vapor will bear. All right. So let us suppose like we have a container, right? And here we have liquid. All right. So it is being heated with some energy source, right? Some energy source with which it is being heated. All right. So obviously it will start to vaporize, right? The liquid will start to vaporize. So if this temperature is constant, right? There will be pressure exerted by vapors. Obviously, if it's in vapor form, it will exert pressure. So there is saturation to that. Beyond a certain point, the pressure, the vapors, it won't be possible to further vaporize the liquid. All right. So that is the saturation. That is saturation. Saturation of vapors. All right. And at that point, the pressure linked to such situation is known as what? Nothing but vapor pressure. Okay. Okay. So if we see its answer, so it's vapor pressure. Okay. All right. Okay. So moving ahead, coming to question number 13. All right. In a fluid flow, if the pressure at some location is lower than the vapor pressure, bubbles starts the bubbles start forming. The bubbles start forming. Pressure is lower than the vapor pressure. All right. What is the phenomenon called? So if we have a liquid, here we have liquid, here we have its vapor. All right. It's vapors. Okay. So as was also discussed in the previous question, like these vapors will exert pressure on this liquid also. All right. Pressure is being exerted. Vapor pressure being exerted. All right. So if this if at some location pressure at point P, and let's call this VP, vapor pressure. So if at some location is less than this, all right, what will happen? The liquid will start to cavitate. All right. So cavities will start to form in the liquid, and such scenario or such phenomenon is known as, in fluid sciences term, it's known as nothing but cavitation. Okay, nothing but cavitation. So if you see, cavitation is the answer. Right? So that is nothing but cavitation. All right. Move to next question. So the next question says the velocity at which these disturbances propagate is known as. Okay. The velocity at which these disturbances propagate. So here these, the context of these is nothing but in fluids disturbances such as pressure disturbances, pressure waves. Okay. So the velocity at which the disturbances propagate in a fluid is known as. So which is known as nothing but speed of sound. All right. So even our voice is a, kind of pressure wave where there are a series of compression and rarefaction. All right. In this way, the sound propagates, and the velocity with which this disturbance propagates is the speed of sound. All right, as the name suggests, the speed of sound. So when we say it's basically fundamentally a pressure wave only. All right. So in compressible flows, we shall see supersonic flows. All right, and how speed of sound plays a very important role, and what is a sound barrier. All right, and Mach, what is Mach number, the non-dimensional parameter, very important parameter in compressible flows, which will define a lot as far as the compressible flows are concerned. All right. So this is also known as acoustic speed also. All right. Okay. Then let's move on to next question. So this was speed of sound. All right. Disturbances. So this has already been discussed. This question has already been discussed. The viscosity of liquids dash with temperature, it decreases, and while that of gases, it increases. This question has been already discussed. So this is the answer. All right. So this question is also complete. 15th question. So now we come to next question, which is related to viscosity, right? So Sutherland's law is applicable for, so whether it's applicable for liquids, whether it's applicable for gases, whether for both or none of the above. So Sutherland's law, it's a fact, right? Sutherland's law is applicable just for gases. And what this law is? So this law relates the viscosity of uh, gases with temperature. So with temperature variation, what will be the effect on the viscosity? The Sutherland's law with caters to such variations. All right. So this is our Sutherland's law. Okay. All right. So the next question we have. So now we are in this session left with the sorry, we are left with the last four questions. Okay. After that, we shall call it off, and then for the next session, we shall meet at same day on the same day and same time. All right, with the same meeting link. Okay. So this shall continue for total 13 sessions. So leaving this till there are 20 such 12 sessions still are left. All right. Okay. So let's see our this question number 17, which is when the fluid velocity is zero, it is denoted as dash condition. So if the fluid is not in motion, what we call it? So broadly speaking, it is fluid statics when fluid is not in motion. All right. And it is denoted as nothing but hydrostatic. Right? Hydrostatic condition. Right? So when the fluid is not in motion, we call such a situation, such a condition as hydrostatic condition. All right. So Pascal's law is also applicable for such conditions only. All right. Uh, this has been covered in week one lectures. All right. So you see the answer. Yes, it's hydrostatic. All right. So if we move on to the next question. The Pascal's law governs the pressure distribution of a static fluid. Just now only I have said this. So yes, Pascal's law governs the pressure distribution of a static fluid, and it's true. All right. Okay. Then 19th question. A fluid is considered as continuum when the Knudsen number is. So in the first one or two slides, in the second slide, fifth topic, I have discussed this. So what has been covered in week 1. So it's the fifth major topic, the continuum, fluid as a continuum. When we define fluid as a continuum, we refer to Knudsen number, all right? So Knudsen number has to be less than 0.01. This has been categorically mentioned in the lecture slides, lecture 2 slides, all right? So if you see 4 options, it is less than 0.01, equal to 0.01, none of the above. So option B is our correct option, all right? The fluid is considered as continuum when the Knudsen number is less than 0.01. All right. So now let's move on to the last question of this session. All right. Answer is less than 0.01. So momentum equation is based on. So like I have already discussed. So momentum equation is one of the governing equations in the context of fluid dynamics. All right. So momentum equation is based on, fundamentally speaking, is it's based on Newton's second law. All right. Okay. So this was it. All right. It's based on Newton's second law. So this is the answer. And so in this session, if I just conclude in starting, just briefly, we revised the topics that were covered in week 1 lectures. All right, 2 week 1 lectures. Then we solved 10 problems that were from a previous year assignment. All right, of the year 2020. And later we saw some uh, fill in the blank or blanks type of questions, which were nothing but the excerpts from the slides of week 1 lectures. All right, and just to revise the concepts that were discussed in the lectures. So we discussed that. All right. So we shall now end this session as the planned questions have been discussed, and we shall again meet the next Sunday at the same timing, that is 3 to 5 p.m. All right. Thank you.